Hello, welcome to this Learn tutorial. In this tutorial, we're going to be answering the question, why do computers use binary? Okay, so you're probably aware that computers use ones and zeros to store and transmit data, and that system is called binary. But why do they use that? Why don't they just use, normal human numbers like 0 to 9 in denary? Or why don't we just transmit information just in letters using our alphabet? Why do they stick to a system of ones and zeros? Well, they don't have to, and some systems, quite specific systems, do use other systems other than binary. But the vast majority of computer systems stick to binary, and there are 4 good reasons why. So let's get looking at those reasons. So reason number 1 is that communication using binary is more reliable than using other number systems. And let me show you why. So let's imagine we had 2 ships and they've come up with some system of communication where they want to send messages when they're, when they're not next to each other. So they came up with a system where they have a light, each boat has a light, and when they want to send a message, this one turns the light on, changing from different brightnesses. From an A, if they want to send an A, they send full brightness. If they want to send a Z, then they change it to almost no brightness. And then if there was somebody, had really good eyes on the other ship, then they could probably be able to send the message, HELLO in different brightnesses, and the other ship should be able to receive it. But of course, it's going to be quite difficult in reality. First of all, the guy who's receiving it might not have perfect eyes, and they might not be able to tell the difference between 26 different shades of, brightnesses, and therefore the message might get corrupted. Also, is you've got other problems. If the boat moves further away, then obviously the brightness that they expected is going to be less, and they're not always going to know exactly how far away they are from each other, so they're not going to be able to understand the message. In fact, it's going to get scrambled because a H, as you move further away, the H is going to go to a G, and all those sorts of things. If I'd go the other way around, I've just realised I'd go to I. Oh well. Anyway, you get the idea. It gets mixed up. Okay, so you're going to have that sort of problem where over an increased transmission distance, then the signal is going to get lower and lower and lower, and therefore it's going to scramble the system. And of course, what about if it's raining, or it's really, really choppy in the waves, or it's misty or something like that? That's going to lower the brightness of the that's going to be received from what gets sent. So if there's any kind of interference, again, with these non-binary system where you got 20 different levels, then the message is going to change. So what do we do to get around that? Well, we use binary, and binary is really, really simple. You have on or off, and an on, if you turn the light on full, it's a 1. If you turn it off, it's a 0. And the great thing about this method is that it doesn't matter how bright it gets transmitted, and it doesn't matter how bright the person, when it gets to the other end, it gets received. So you could have interference with waves, they can move closer or further apart. It doesn't matter, because the guy looking out for the flashing light is either going to see on or off, and you don't really care about how bright it is. So it makes it incredibly reliable. So reliable, in fact, that that's actually what boats still use. So back in the 1800s, these signal lamps were developed and used in conjunction with Morse code, which was also developed in the 1800s. Then a series of ons and offs can be transmitted, and these can be translated from the ons and offs in light and get translated back into letters. So that's a very reliable system. Now, in theory, it is slower. It is slower than sending just one particular brightness for any particular letter, but in practice it's that reliable that you can't use the other system anyway. And the same applies if you start sending signals with computers. So for instance, if you send data along a telephone wire here, which we do when we connect to the internet, or if you've got a fiber optic connection, then the same system applies. When you send electricity along the cables, the further it goes, the signal gets reduced and reduced and reduced and reduced. So much in fact, that they need to have repeater stations every few miles just to boost the electrical signal. Same with fiber optic. When they send light down the lines, then again, it needs to be boosted. But the good news is that with the electrical signals that get sent out, there's either an electrical voltage or there's not. And with the fiber optic, there's either a light shining down there or there isn't. It doesn't really matter how bright it is. It still gets sent through. So communication is much more reliable using binary. Okay, and it also is more reliable as well inside of the actual device itself. So communication just doesn't just happen when you're sending it from one device to another or getting information from the internet, but also is when your device itself is made up of lots of different components and electrical signals need to be sent between those components. By sending them in binary, just on or off, you get around a lot of the problems with electrical signals because voltages aren't stable. When you connect to the power network, when you've got your computer plugged in, it's connected to the power grid, but that power grid isn't stable and it's certainly not perfectly stable. So your computer needs to be able to cope with that instability. Also, if you've got a mobile phone, as your battery dies and it gets lower and lower, the voltage dips on your phone and it becomes more unstable. Binary can cope with that because it doesn't really matter what voltage it's coming through. It doesn't need to be exact voltage. It will still work. So that's reason number one. Reason number two is that storing data in binary is also incredibly easy. In fact, before we even invented computers, they were storing data in binary format. When the Industrial Revolution happened and they were setting up the looms to make all these different textiles, they often used large punch cards which programmed the looms to make different patterns. And then when we got into the 19th century, these punch cards, they were taken up and they were used by the first computer manufacturers. So here, this is a punch card from the middle of the 20th century made by IBM. And it's a very, very simple system. You have a card and you punch holes in the card where you want ones or zeros to be, wherever the data is, whatever you're storing. And when you put the card into the machine, it runs a light through the card. And when it gets to the hole in the punch card, it lets light through. So that would be a 1. And when it's blocked, it won't let light through. And therefore it's a 0. Again, it's incredibly reliable because it doesn't really matter how bright it is. It's either letting light through or it's hit the cardboard and it's not letting light through. So it makes it incredibly reliable and really, really easy. You don't have to convert the 1s and the 0s that are stored in binary into any other format. They natively sit in the 1 and 0 format that would work on the punch card. And as things got developed, then the same applied for all the different systems that we store data on. So for instance, CDs and DVDs, it's the same concept. You have, it's no surprise that this looks like Morse code. On the surface of a CD, if you zoom in really, really close, you can see pits and flats here. And all the laser does is the laser shines down, and when it bounces back, it either triggers the laser detector, in which case it's a 1, or it doesn't trigger it. And it doesn't really matter about how deep it is because you've either got a flat or you've got a pit. And the laser detector will be able to detect what's known as that phase change between the two. So if you've got CDs that are manufactured by slightly different manufacturers, or they've got slightly scratched or something like that, then it won't matter because although the pits and flats might not be all exactly the same height, you've either got a pit or you've got a flat. And you can detect that really, really simply. And the same goes for hard disks. So magnetic hard disks, the older technology, similar sort of concept, but instead of using pits and flats and actual physical changes to the disk, what it does instead is it has a little read-write head here, and right on the end, what it does is a little read-write end on this actuator arm, and it scans that and it reads this platter looking for magnetic polarity. and it can detect whether it's a north or a south, which way the polarity is going. And when it wants to write data, all it does is send an electromagnetic pulse that overwrites that charge. And again, it's really reliable because it doesn't really matter about how much the charge is, whether it's strongly going to north or strongly going to south, it doesn't really matter. As long as we can detect which direction it's going in, we're not particularly concerned about the magnitude of the polarity. And so again, it's really reliable. Also, is storing the data. There's no real transformation here. Or you can set it so that all the norths are ones and all the souths are zeros, and that data just immediately can get sent onto the disk and stored and read. There's no conversion. So that's the second reason. So reason 3 as to why computers use binary. Well, computers use binary. In fact, we use electricity because electricity is incredibly quick. So we're using electricity. We can have computers that can do many, many calculations really, really quickly. But in order to do that, we need to be able to use a system that works well with electricity, because otherwise we're not going to be able to use an electrical computer. We'd have to use a mechanical computer, like the Babbage machine, which is much, much more slow. Okay, so to use electrical computers, we need something that works really, really well with electrical circuits. And if you think about it, electrical circuits, really, what we're talking about here is turning, the simplest interaction is turning a switch on, in which case it connects the circuit, or we turn the switch off, and that disconnects the circuit. And going back to the telegraph, when that was invented in sort of the 1840s, so that system was really, really simple. It was just a switch. You press the trigger down here and it connected the circuit. It sent an electrical pulse down the line, and at the other end that activated an electromagnet that made a buzzer, or either made a buzzer work, or it did something else that allowed it to record, or allowed somebody else to listen to and understand that Morse code that was being sent. So again, electrical circuits, they just use on and off is the simplest form of electrical circuit. So something that works well with that, natively with that, without having to do so much work, is going to work really, really well. Ons and offs. So electrical signals, they're used on and off. Binary works really well with that. And what happened over time, as computers got developed, we started to develop transistors. And transistors are a kind of switch, the electrical switch, that you can switch on and off really, really quickly. And these transistors can be combined into logic gates, and lots and lots and lots of transistors are what exist on today's silicon chips. And that's really, really important, because if you combine transistors together, you can form logic gates. And then as you combine all these logic gates into different logic circuits, then you can create an actual computer, the functioning parts of a computer. So for instance, you can create an adder that adds two digits together, ones and zeros together. And if you combine those together, lots of adders together, then you can add up large numbers. So using logic gates and logic circuits, you can do all sorts of things. You can add numbers together, you can subtract them, you can divide them, and you can also do conditional logic. So you can use logic gates to compare two values. And through that, you can do a conditional program where you can say, okay, if this, do this, otherwise do this. And then you can send it to different memory locations in the computer, and then you can get it to loop and do all of the other wonderful things that computers do. Okay. Which brings us on to the last reason, is that through the use of these circuits and through the use of binary, you can do quite a lot of really, really clever mathematical tricks and operations that you can't do very easily in other number systems. It's important to remember that computers, the prime job of a computer really is to compute, to calculate, and to give some kind of output. Every time I move my mouse on the screen, all it's doing is it's taking my input from the mouse, working out what direction I've moved the mouse, and then it's calculating the new position of the mouse pointer on the screen. Okay, and your computer does billions of calculations per second, especially if you're playing a 3D graphically intensive game. Everything is a calculation, so it needs to be able to do this really quickly. And one example of how the computers can do these calculations quickly is how binary can be used to do multiplication and division. It works really, really well. If you're trying to say, let's say, for instance, multiply a number by 2 or anything that's the power of 2, like 2, 4, 8, 16, you don't have to actually do the calculation with those bits. You take the original number, so here's the original binary, and that's stored as number 26, and then all you do is you apply some logic to them where you shift every single one of those bits 1 to the left. So here, the one that was here goes here, the one that goes here is here, and the one that was here goes here. And now what you've managed to do there, just by shifting the bits to the left, is you've doubled that number without any real calculation, any real effort. And that can be done very, very simply using transistors. And again, if you want to, double it again, or you just literally shift them 1 more to the left again, and it will double the number once again. So you can do these calculations incredibly quickly. And of course, obviously, it goes the other way if you want to do division. And you can do more complicated multiplication and division as well by combining multiple different versions of shifts and using adders to add up digits as well. Okay, so binary, you can do a lot of really clever tricks that allow the multiplication and all the other calculations and computations to be done quite quickly and simply with it by the computer in binary. Okay, so those are the main 4 reasons why computers use binary. So it's more reliable, number 1, to communicate both within the device itself and communicate between devices when we're using networks and transmitting data. Storing data is incredibly easy in binary. It works really well with electrical circuits because binary is just on and off, and the simpler circuits work really well just on and off. And there's a lot of mathematical tricks that can be used to make mean that calculation and computation can be done incredibly efficiently and quickly using binary. Okie dokie. Thank you very much. If you've liked the video, please do like it. And if you want to, subscribe to my channel. Thank you very much.